Last day of Unit 6. Let's see how we do. So now we're going to talk about finding higher order derivatives, which we've already discussed how to find like first and second derivatives, but this is really going to be with the implicit differentiation more than anything that we need to focus on. So when we answer the second derivative, this is what I really want you to answer here is with the second derivative for implicit. So we've kind of already, like I said, discussed like, hey, just derive, and like that's pretty easy when we're in implicit. None of that was too difficult. We even discussed the relationship between position, velocity, acceleration. But we're going to talk about the second derivative in this notation. So this is the implicit second derivative, and that's what we really want to kind of talk about. So if we review a little bit just from some explicit, remember like the first derivative, second derivative, we can either do this or we can put a 2 here in the parentheses. Third derivative, we can use the Roman numerals here. Or if I did the third, it needs to be in parentheses. And then the fourth derivative, I can use Roman numerals, or I can do the fourth, which is now 0. So just a little bit of review on that. See what you can find for this. See if you can find a pattern to get this without having to write all of the derivatives. Okay, and I just want to challenge you guys to see if you can get the right answer here. If not, ask me in class. Okay, so here is the implicit differentiating for finding the second derivative. So the first thing you have to do is what we've already learned, and that's go find dy dx by itself. So we've got to do that first. We've got to get the first derivative out of the way. Once I have that by itself, all solved for, no other dy dx is involved, then I can take the derivative of this. So the derivative here of the dy dx becomes that d squared y over dx squared. And when we take that derivative, usually we're going to see a dy dx involved again. So then we're going to use what we have already solved for in part 1 and go replace all those dy dx's, and then we'll find the second derivative. Okay, so let's do an example. Here is my equation. So the first thing, it's asking me to find the second derivative, but the first thing I'm going to do is find the first derivative. So that's a power rule, but I took the derivative of y with respect to x, and this is just 4x, so it's linear, so it becomes 4. So then I'm going to go solve for dy dx. So this is all step 1. And this one I'm going to rewrite to use a power rule. Okay, so now I'm going to take my second derivative since I have the first derivative solved. So this becomes negative 2 y to the negative 2 dy dx. So that's negative 2 over y squared, and dy dx we already saw was 2 over y. So that's plugging in for dy dx what we know it is. So this would be negative 4 over y cubed. So that was kind of like step 3 is plugging in and getting it by itself. Okay, so overall, the second derivative is negative 4 over y cubed. Okay, this one wants me to solve for the second derivative when x is 6 here. So let's go ahead and get the first derivative knocked out. Try this on your own and then just kind of check with me as you go. Everybody see product? It's almost always there with implicit. And then the derivative of the minus 9 becomes 0. These guys we're going to keep over here. This one we're going to keep over there. So I got to just move this. So this is what I got my derivative down to for the first derivative. So there's my step 1. Okay, step 2, I now can take the derivative of this. Now I have the quotient rule. Low d high minus high d low all over low low. Now, I have some options of what I can do. I can go ahead now and sub in all of the dy dx's like we normally do and try to get that value that we want. But here, I'm looking when x is 6. So let's go talk about when x is 6. So when x is 6, I try to go solve for this. That is a perfect square. So I have the solution of 3 twice. So I actually know that I am plugging in this point. And it is so much easier, you guys, instead of replacing these, to actually go back up to that first derivative and go find the numerical value. So if I want, here, let's use a different color. I want to find like dy dx evaluated at that 6, 3. So that would be 3 over 2 times y is 12. Oops, y is, oh gosh, sorry. 2 times 3 is 6 minus 6. Oh, look at that, you guys, it's undefined. So I can't even get the second derivative. I get an undefined answer. Okay? But if we did get an answer, we could go just plug it in when we wanted to, and it's super cool. So let's try to think through that as we do the next one. This is from an AP example. So consider the curve given by this equation. And what if I only gave you like the y? Could you find the x on your own? So if I said like 1 minus x times 1 equals 2, and then negative x equals 1, so x equals negative 1. So just to kind of think through, if they only gave you one piece of information, you usually go plug it back in to find the other one. But they did give us both here. And look what they already did. They gave us the first derivative already. Thank you. Okay, so I want to find the second derivative and then plug in this point. So let's go find the second derivative. So I can see that I have a quotient rule. Low d high minus high d low all over low low. So I am looking for this d squared y over dx squared at this value. And so instead of subbing all of these in, again, let's go back up and use that first derivative. So what was dy dx evaluated at this point? So y would be 1, 3 times 1, minus the negative 1 would become plus. So I can see I'm going to plug in the 1/4 anytime I have a dy dx. So this one is now 3 times 1 squared is 3, minus a negative 1 is plus 1. And then times what we just found this to be is, oops, I was going to do this color, help us remember, is the 1/4. Minus, the y was just 1, 6 times 1 is 6, times, again, we found that one right there to be 1/4. Minus the 1. All over 3 times 1 squared is 3. Again, plus, since it was minus and negative, all squared. And simplify that down and see if you can get 1 over 32, because that could be on a multiple choice. So that's a little bit easier instead of like replacing and rewriting when you're looking for the number only to use that first derivative to plug in the number from there. Little trick of the trade. Okay. Here is one review with the e that we already know. So I'm going to take my derivative of y. E, we bring e over just like we see it. But then I have to take the derivative of what was up there, so that would be 3x squared and multiply. Okay, now I want to do the second derivative. This already has dy dx solved for. Now I see a product rule. The first times the derivative of the second, which we kind of just did, plus the second times the derivative of the first. I'm going to factor out a 3 and an x and an e to the x cubed. And then let's see, I took out a 3 and I took out 1x, so I have a 3x cubed plus 2. Well, let's see if it wants us to match though. Okay, so if I look, they did take out an x when they factored, so I have to go put that back in and just leave this guy out. And then that would be 9x to the 4th plus 6x, and now I see it as D. So multiple choice, we just got to get to where we can match. Okay, so do you remember when we talked about if we're concave up, tangents are below, and when we're concave down, tangents are above? Well, now I'm going to tell you how to know concavity without looking at the graph. When the second derivative is greater than 0, f of x is concave up. So if we can say that second derivative is greater than 0, kind of like how we did here, the second derivative at this point is greater than 0. So we know that f of x is concave up at that point that we just plugged in. Okay? And when we are concave up, again, we said tangent lines are underestimates. And then flip-floppy, when our second derivative is negative, f of x is concave down, shaped like a frown. And so tangent lines are overestimates. Let's do a really good example now. This is from 2017, and we're going to do both parts A and B. So, at time t equals 0, a boiled potato is taken from a pot on a stove. So we've talked about this one before, and we actually found the equation of the tangent line. So I want you guys to see if you can go get part A and do all of that, because we've done part A exactly before. So just kind of bringing it back around to see if you can do it on your own again. And on part A, want to see if you can get this tangent line. Some of you may say, I like it to be in terms of my h and my t, and that's fine, either one. But then h of 3 is approximately this guy. So we went and we used a tangent line to find an approximation. So what do you think we're going to do if we're finding the second derivative now? We're going to go see if this approximation was an over or an under estimate. And how do we do that? Well, we go see if the second derivative is going to be either concave up or concave down, and that's going to let us know. So positive or negative second derivative. Okay, so in B, And please, 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 do not just copy me. Actually go make sure you can do that. All right, pause me if you have to. Okay, so part B, find the second derivative. So the first derivative was this right here. I'm going to go ahead and just distribute. I think it makes life look easier. Negative, negative, positive. And yeah, so that's a linear. So when I take my second derivative, that's just negative 1/4, right? Wrong, because we took it with respect to x. So this is implicit differentiation. Do not forget this, and this is the biggest mistake. I actually graded this problem as an AP grader, and a lot of kids forgot that, and I was like, no, but I know you won't. Okay, so now we're going to replace what that is. So we said that that was negative 1/4 h plus 27/4. And d squared h over dt squared now. I'm going to go ahead and just do that as well. Distribute 16h minus 27/16 now. And that looks ugly to me. I'm going to pull out a 1/16. And that looks a little bit easier for me to kind of work with. So what are they asking? They want to know that was that estimate we just found when t equals 3 up here, was that an over or an under estimate? So what point were we using in part A? Do you remember what we evaluated at? What point? So we evaluated at that point 0.91. So we have to do that same point here. And the second biggest mistake that kiddos made is they tried to plug in a 3 for the h actually, but so if we ever plugged in a 3, it'd be at the t, but that would even be wrong. That's what we're approximating. We have to go, what did we use to make the tangent line? And we used that point of 0.91. So that's what I have to plug in here to this guy. Remember, this is t and this is h. So there were no t's to plug in. And you can simplify that if you want to, but that's a waste of time because I know that that is greater than 0, because that's going to be a positive number times a positive number. Therefore, I know that my function here is concave up at that point. Therefore, the tangent line approximation in part A was an underestimate for that t is part, like t equal 3. Okay? Okay, we are going to do one more together. This was from 2012, number 5, and we're just going to do parts A and B. Okay, the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight, and at time equals 0, the bird is weighed, and we get 20. So I know at time equals 0, we're at 20 grams, and B of t is the weight. So we have t and B of t, or you could just say B. And here it gives me the first derivative. Okay, so it says let y equals B of t be the solution to the differential equation above, la 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 la, with this initial condition. That's what we just wrote, that point. Okay, so it's just giving us what we've already got. And it says, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? So remember, this is the first derivative. So it's talking about how fast the weight is changing with respect to time. So how fast the weight, that's the dB, is changing with respect to time. So I'm going to go on part A and plug in that dB dt when I have the B of the 40. And I'm going to go plug in that dB dt when I have the B of the 70. And we're going to see which one is bigger. Here, I kind of made this one all over the place. Because if we have a bigger number, it's talking about a faster rate. So this is 1/5 times 100 minus, so that's 60. And this is 1/5 times 30. And you don't even have to simplify to tell me that the dB dt at 40 is greater than the dB dt at 70. So it's gaining weight faster when it's 40 grams than when it's 70 grams. And that kind of makes sense. Like when you're a baby bird, you're going to grow really, really fast. Think about even just a baby. Their weight like grows really fast, and then into adulthood, hope that your weight's kind of steadying out. And here you can see like it's just going to steady out. Okay, B. Go find dB dt, or sorry, the derivative of dB dt. So the second derivative here. So let's do that, and then we'll go to the second one. And it only wants it in terms of B. That just means don't leave any first derivative dB dt's without plugging in things, which we know. All right, so we're going to look at this derivative, and again, I'm going to just rewrite what dB dt looks like. So that's 20 minus 1/5 B. So I just kind of distributed the 1/5 to both. So let's go find that second derivative. So this is linear, so it's just the negative 1/5, except I took the derivative of B with respect to t. Do not forget the implicit part. And now I'm going to rewrite that. So plugging in what dB dt was. And I like to see things easier, so that's what? Negative 4 minus 1 over 25b, that would be plus. Okay, and I'm going to go ahead and take out that 1 over 25, which means I need to, let's see, that would be b, and then multiplying would be minus 100 right there. Okay, so that makes it easier for me to see what's going on. So there's my second derivative. It is up to you on how far you simplified it, but for me, I just like to see it. You might just like only do this piece on the on it and just like bake your answer and then kind of go do some work, okay? So here it says use that second derivative and explain why this is not the graph. Okay, why could this not be the graph? So if I look at this, second derivatives talk about the concavity. And if I look, I see I'm concave up, concave up, concave up till about right here. And that's a point of inflection. And then I'm concave down, I'm frowning until about right here. So somewhere in between a weight of 20 and 100, I've switched between concave up and concave down. But here, I can see that from time like weight 0 all the way up until about weight 100, I'm going to be negative. Do you see that? All of those are going to be negative answers, which means that we should be concave down on this interval. But that is not true. We were concave up for part of this interval of weight. So however that graph shown was concave up and concave down on 0 to 100. So it cannot be the graph. Okay? All right, kiddos. Well, we have finished up with this unit. Going to be testing for break. It's going to be great. All right, see you guys in class.